Okay. Okay, so maybe just to summarize what we saw, we started here with V's. Now we saw that we can just replace this with gradient fields. It makes the formulation somehow a little bit cleaner, maybe in some sense, of course, easier. And so another way of saying this, in this area, sometimes they speak about minimizing movement schemes, right? So remember we had the curve rho t. So we can ask for a vector field that reproduces this curve like this. And if we want to have the vector field to move as little as possible, then we should take a gradient vector field here, and this choice is going to be in some sense unique. I think I stated this result that you can always find a vector field. There was a, so you can find it for almost every, so for Lebesgue, almost every point in time, but it's just, so, okay, I'm skipping some technical details here, right? Okay, so gradient fields sort of minimize the movement in this sense, in the sense of minimizing this L2 types cost function on the velocities. Okay, yeah, so now we're going to, okay, I don't know. I should write it down, eh?
Yeah, I guess so. I don't know.
Let's try. Okay, so we're going to come now to the Riemannian structure.
We need to try with another one.
No.
Then with the, so maybe with the tissues. Yeah, the tissues.
Okay.
Work better.
Like this? Can you see it?
Yeah, yeah.
Okay, so, I mean, okay, so this development was kind of a preparation now to set up this Riemannian structure, this auto-calculus type of thing. That also Juan already explained, right? But I'm kind of coming from the other direction, like starting from here. And so let's sort of make a very small crash course, Riemannian geometry, right? So we say, so people write Mg is a Riemannian manifold. And so that means okay, so the manifold is a kind of a curved space, and so for every point in this space, this means that there is an inner product, a scalar product, on the tangent space. So you should think, okay, it's like a sphere. The tangent space, the tangent space is a plane that touches the sphere, and then this is this plane, and we want to measure angles and lengths of vectors in this plane. Okay, and okay, we've got a way of doing this at every point, and as Juan nicely said, maybe we want to do it differently in different parts of the space. And so from a computational statistics point of view, maybe it makes sense to do something else in different regions of the space, right? So do something which is a bit adaptive, maybe. So this defines a scalar product. And okay, so this is the length vector v in this plane. Okay, and then so naturally from this, we can define a metric on the manifold. So this sort of naturally leads to a distance or metric. So that's induced by this Riemannian metric. Okay, so these are y and z are points on the manifold, and we can, so this is the manifold M, there are 2 points y and z, and we want to say what's the distance between them, and we say that the distance is the length of the shortest connecting curve. So we look at curves, and we try to find the shortest curve, and the distance is going to be precisely the length of this shortest curve. So write it like this. Sorry. Yeah, it's infimum over curves x. So these are infimum over curves x. So I'm considering curves parameterized by some time index between 0 and 1, taking values in the manifold, like a curve like this.
Okay, so that's g subscript x, not lambda.
Yeah, exactly. So, okay, let me write it. So, yeah. Okay, so we had y, we had z, we have y, we have z. We look at curves x. So this would be one type of x of t, but then we get another one. So we consider it's a big space, right? But we only consider curves that start at y and go to z. And this is the length of this curve. We need to look at these Riemannian metrics evaluated at the point where we are, and then we look at the length of the tangent vector to the curve, so which is the derivative. Okay, so that's we can have this. That is something, and somehow the point, of course, now of writing this is that this looks a lot like this already. So if you have got this intuition, then we can kind of try and rewrite this a little bit to make it look exactly like this. And then we have this interpretation that sort of this is one probability measure, this is another one. So we think of measures as points in some infinite dimensional manifold. And we look at curves, but these curves are also curves of measures. So we're looking at ways of deforming one measure into the other measure. This is somehow the idea of this. And okay, so one important remark, I guess, that this is also, here it's a little bit annoying. Maybe I'm going to write here the square, and I'm going to write here squares. It's going to be helpful. Now, so it's a little bit of an annoying formulation because of this and this, but it turns out that this is going to be the same if I so I'm putting sort of this square into here and cancel the square root with the square. And it's going to be the same. I mean, it's not, so for one given curve, it's not necessarily the same expression. But if we do the infimum, then it's going to be the same. And so what this does is the following. We can say, so this is the length as I said, right, this is the length of a curve x. So we've got a curve x, we can measure the length, and so this is sometimes called the energy. And okay, so there are two. So this is a little bit non-trivial here. And okay, why is it so? So first of all, so there's two things to note. So this functional L on curves is reparametrization invariant. If we reparametrize the curve x, then the length is going to stay the same, because we're just measuring the length of the curve, and it's essentially, so it depends only on the graph, or on the range of this curve, right, and not on the way it's parametrized. So I'm just going to write it like this. And this is some reparametrization. And then the second one is that by Jensen, so of course this smells very much like Jensen. We always have this, and we have equality if and only if if this is constant. So, right, by Jensen, we can bound one of the other, one in terms of the other, by putting the square in and then canceling it, so against this integral. And this is going to be an inequality like that. But if this is in fact constant, then it's going to be the same. And this is an if and only if, right?
Constant as a function of
t.
Of t. Okay.
Right. So does it make sense? Yeah.
Yeah.
So if as a function of t this is constant, then it's the same. And if as a function of t it's constant, then this means it's sort of parameterized in a natural way. So the speed of the curve is always the same.
Yeah.
And we parameterize it in such a way that it's always the same. So it's nice if we have a parameterization like this, nicer to think about and do calculations with. And if you see these two things, then so minimizers of E are also are always minimizers of L, because if we have a so if we have a curve that is not parameterized according to this, then we can reparameterize it, and this will make E smaller. And it will then be the same as L. So minimizers of E are also minimizers of L. And the beauty of minimizing E instead of L is that if we do this, then automatically we get this nice parameterization. So if we minimize instead this, then we got a huge non-degeneracy. We get lots of solutions which are essentially the same, because they can be reparameterized and end up the same after reparameterization. But if we minimize this instead, then we automatically get a curve that has a nice parameterization. Okay? So that's why it's somehow, in some sense, nicer to do this instead of this. And as you can see here, this goes some way towards this, because here we don't have square roots, and we have sort of the equivalent of this. So we're going to work with this energy kind of thing. Questions? Oh. Okay, so
Nick, I got to the length one, right? Not to the energy one.
yeah, I think you got to the length ones. Yeah.
Normally they give it's always usually in the energy.
Yeah, they like to put it like this because it's a little bit more convenient. Yeah.
So sorry, I said that. What I wrote down was very convenient. It's actually that one.
Yeah, but it's the same.
Yeah.
So, but yeah. All right. And so, okay. maybe I'm just going to keep this. Okay, so now the issue is kind of, I mean, here we are minimizing only over this curve. And here we are, it looks like we are minimizing over two things. But sort of given rho t, also this nabla phi is kind of determined uniquely, right? So it's basically the same thing if we just suppress one of these in the notation, let's say. So I'm just going to suppress this in the notation. And write it like this. It's okay. Here we define now this Wasserstein tensor. And so we're trying, let me just write it. Okay, so this kind of defines this in terms of this. And so precisely this means this. Okay, so this is somehow trying to make a connection to Juan's lecture, right? So here, now we're thinking only of these curves rho, and in terms of their derivatives, like here. And so these tors should be sort of, so maybe I'm going to write somehow like this. So Juan wrote this. So these are possible changes to the density, such that the density remains a probability measure. Right? So that's why it has to integrate to 0. And so this is what we are going to ask of these. This is also going to be true of these derivatives, because rho is a curve of probability measures. Right? And so we calculate this like this, and phi is given in terms of tau by solving this equation. So I think this was like this. Yeah. So if you've got two changes in the density and you want to compute the inner product, so which kind of tells you the angle between these changes, right, in this geometry, then you have to first of all solve this equation for two. So there can be primes here, right? For two different things, and then you can compute this. And this looks a little bit, yeah. I mean, this looks a little bit, it looks a little bit complicated, right? Because you have to solve this intermediate equation. And so that's why there is different, somehow, let's say, conventions in the literature. So this is one way of thinking about this, tangent space. But then you have to define the inner product in terms of this equation. Or you can think that, what I'm kind of doing here in this lecture, right? It's this space, but I'm doing it because it kind of arises from this Helmholtz decomposition, right? And so the spirit is that you think of the way a density can change. You say that the density can change by pushes through gradient vector fields. And then these changes should be, if you want to compute the angle between two changes, you do it like this. And this equation establishes sort of a one-to-one correspondence between this and this. This is a slight lie, because so for any phi, you can certainly compute tau. Also, this will always have mean 0, because as one said, if you integrate and do integration by parts, it will have mean 0. But on the other hand, you can ask the question of whether for any tau you can find a solution here. And that's not, so that's kind of true, because somehow the range of this differential operator is always dense in L20 weighted by rho. If you have here 1 over rho, it's like the Poisson equation. And if you have a Poincaré inequality, then you can always solve this equation. So but on this heuristic level, we just think that this is a one-to-one correspondence. So, maybe the last remark is not very important. You just have to think that this is a one-to-one correspondence between this change that you can apply to a measure and this kind of change that you can apply to a measure. And one of them is pushing it with the gradient field. Remember Helmholtz decomposition, we restrict our attention to gradient fields. And here we look pointwise. Right? So that's sort of the idea. Okay. Somehow the spirit of this, let's say the Otto spirit, is whenever you have a curve, so whenever we have a curve rho t, we are meant to think about it as in this form. So for example, right, if we think about the heat equation, then this is not in this form. So if we think about solutions to the heat equation, it's not in this form, but we can just write this. So introducing this score, right? And then this phi is going to be log rho. And so thinking of the heat equation like this is kind of the Otto calculus idea, let's say. I guess this is sort of one of the things that Otto originally spotted or somehow championed, right? So this, let's say this observation. Yeah.
So can you interpret the heat equation as an optimal transport problem?
So you can interpret it as a gradient flow, right? So this is this phi, and furthermore, so we have KL between rho and pi. So this would now be Lebesgue. I guess if you define this. So this is sort of behind this interpretation. So this spirit means that we should always think of these equations in this form. And furthermore, when we want to go to gradient flows, it tells us what this phi should be if we want to make a gradient flow. So in particular, if we have the entropy, then somehow the statement is we need to compute this type of functional derivative, and we plug it here, then we get back to the heat equation. And this means that in this Wasserstein sense, in this Riemannian geometry, this is a gradient flow with respect to of this with respect to this. This is sort of the statement. So it's not, I mean, it's not really optimal transport, but it's sort of a gradient flow in this optimal transport sense. Yeah.
Why are these two equal to each other? I think I'm missing something.
Which one? This one or
The delta rho is equal to.
this one?
Yeah.
So if you take here the gradient of the log, then you get grad rho over rho, then you cancel the rho.
Yeah.
So
Oh, right. I see. Yeah. Okay.
now you cancel this out, and then you get this.
Okay. Okay.
So this is kind of this trick, and yeah. And so if you have a curve like this, you are meant to kind of massage it into this form in order to use this idea, right? And as we discussed in the beginning, you kind of always can do this. It's just maybe not. I mean, maybe there's no closed form solution, but so for any reasonable curve, you can somehow write it in this form, and then that's called the Wasserstein velocity in some sense of this.
Doing the same trick for the Fokker plank of the Langevin diffusion. Because I turn the Laplacian and the drift are all together looking like that.
Right.
The log ratio of the time and the
Right. Yeah, other questions? So this is maybe, of course, kind of an important bit, I guess. Yes, I kind of have to speed up if I want to do anything, if I want to do everything, but it doesn't, it's okay, right? I just stop when I stop. Yeah, okay. Let me see. Okay. Like one point is that, okay, so until here we've kind of developed this way of looking at it. Now there's a very important computational thing. I mean, Juan already stated it, and I'm just going to restate it because it's important. So Juan said that if you want to have a gradient, then we need to have a metric. And somehow, if we've got a, like in Riemannian geometry at least, there is a gradient operation associated to the G. So when we have a G, there's going to be a gradient operation, and any different G introduces a gradient operation. And so we can discuss how this exactly is, but I mean, the easiest thing is to just say that we've got a, oh, maybe I can get rid of this, but the easiest thing to say is that there is a formula for this. And so, like in, okay, so this is what Juan wrote, and it means really, so we can do this because this is this, and this is defined. Do you know this? It's defined in terms of. Maybe I should go through this carefully because it's important, right? Okay, so if we have like a functional, like this one, or like this one, and we can do this. Okay, so we want to compute some sort of derivative, so we make a small perturbation. Maybe I use a different letter, somehow lambda or I don't know, alpha. Alpha is something that can perturb rho, so it should integrate to 0. We can look at this. So it's a directional derivative into direction alpha. And we can request that it's given in this form. So this is meant to define this. And it's like in the usual gradient setting, the directional derivatives can be given as a scalar product with respect to the gradient, something like this, right? And so this defines this. And if you go somehow through the calculation, so this is how you would arrive here. You can write this. Then here, instead of rho, I put rho plus epsilon alpha. I take the derivative. I set epsilon equal to 0. And then then it will look like this. And then I just identify this with this. Right, and so this is sort of the calculational way of doing it. Whenever you've got a functional, you go through this motion. You identify what this is, according to this. And then you just write, then you can write this. Sort of the W2 gradient of this. And then you use this formula. So we're using, instead of this, we're using this. The minus cancels with this. And then we do this. Okay. And in the specific case, when F is the KL divergence between rho and pi, then this will look like this. When we do this, so, and then and this is the usual Fokker-Planck equation for overdamped Langevin. So this is an extension of what we said here, that or what Juan also said, right, that the field equation is a gradient flow of this, but the overdamped Langevin dynamics, or the Fokker-Planck equation related associated to it, is a gradient flow with respect to the KL. This has two terms. One is this, and then this, where pi is e to the minus v. If you write out the KL, you get two terms, one of this, which we already have, so you get this. Then you get a second term, and you get the drift term in the Fokker-Planck equation.
Should it just be log rho pi in that fraction?
Oh yeah. Like this, right? Yeah. Sorry. Yeah, thanks. Yeah, I don't know. Are you happy with this?
How did you go from the gradient with respect to the Wasserstein? Like, is that specifically for this step, or like how?
You mean from here to here?
Yeah, like is that like just from definition of the Wasserstein gradient for the metric?
So in geometry, so if you place yourself in geometry, right, on a manifold without a metric, like if this is a manifold, and let's say you have got a function smooth, right? Then you can compute df without any additional structure, without any metric, right? It's in the cotangent space. So the problem with this is that if you want to write an equation like this, it's not really possible. So this is in the tangent space. on the tangent bundle. This is, if I do the D, this is going to be in the cotangent. So this kind of equation doesn't really work. And you need to somehow translate from the cotangent space to the tangent space, and the metric identifies it. So the metric gives you an identification if there's a bijection. And this bijection has a concrete form. So so it's kind of like this. Yeah, you use the in coordinates you kind of have to compute the gray. You have to compute this, and then you use the components of the metric tensor and have this kind of equation. And it's the same. So this is sort of also what Juan wrote here. Where is it? I delete. Oh, it's here. I mean, you can also motivate this more and so on, right?
Yeah.
Maybe I can do it in the break. But here, so this is exactly this. And if you put things together, so this was this kind of operator. And this naturally generalizes this. And so in this way, you get this, right? So this, I mean, this whole operation here, right? This is this Wasserstein gradient.
Delta was what I kept calling.
Oh yeah, so how did you call it? Like
The first variation. I don't know, I see some people calling it that.
yeah, the first this right, the first variation. Yeah.
I've seen other places sometimes that they identify the Wasserstein gradient with just grad of the first variation.
You mean this?
Slightly differently, right? Yeah.
Yeah, this is because they say that. So if you take this perspective that somehow this is the Wasserstein velocity, because you're meant to think spiritually in terms of these curves like this gradient field, then this is can be identified with this, yeah. Only. But then you so this identification is essentially between gradient fields and changes of the density, which is through this divergence operator.
And right now, F is just anything, or?
Yeah, here F can be anything except, of course, for regularity, right? Yes. Okay, so yeah. So yeah, coming back to what's this time say? Do you want to break?
It depends on how it breaks up the lecture. I think we haven't been going for super long this time, but if the remaining bit sort of is its own self-contained thing, then
So okay, let me do one or two more bits, like small bits, and then we break, right? Okay, so but this gives you kind of, I mean, this is sort of a mechanical way of coming up, like also what Juan said, of algorithms. You can, for example, replace the KL by something else, and then you calculate it like this, then you get a PDE of this sort. And then again, we have the problem that maybe we can't implement it, right? But we can think of whether we can implement it. Okay, one little side note that I think I should maybe skip in the interest of time is that this kind of equation, this can be thought of as infinitesimal optimal transport. So you can see it kind of here, right? So this is kind of how to transport. If you think of here, we've got two different measures, mu, and we can ask how to transport one to the other. But let's say we want to linearize it by just saying mu and nu are kind of close. Then this is a sort of maybe an easier question, right? If we can linearize something. And so the transport problem from mu to nu can be described by the Monge-Ampere equation, which is a highly nonlinear PDE. But if we discretize it, if we linearize it, assuming that nu is a small perturbation of nu, then we get to this linear PDE, which is this Poisson equation. And I think it's interesting and somehow, right? And it kind of makes sense because here we are chopping up the complicated global nonlinear problem into sort of more tractable, somehow smaller subproblems at the expense of maybe minimizing over all of these subproblems. Okay. Yeah. Okay, so now we said that we can change this KL. And I want to go back now to this comment that in the beginning we said we had this Helmholtz decomposition, and when doing this we made the choice that we established orthogonality with respect to the L2 inner product. And this was sort of the only step where something where there was a sort of arbitrary choice in some sense. Everything else is in some sense natural, right? So this is kind of this continuity equation is sort of holds for kind of everything and so on, right? So it's kind of general and natural. And now I'd like to just comment on what happens if we choose different if we choose different notions of orthogonality. And we can then just go through everything and replace everything everywhere the important bits, right? And we're not going to do everything in detail, but I'm going to point out the results. So first of all, here, this form, this arose because we chose the scalar product at this specific Helmholtz decomposition. So let's go back to the V. Okay. And so before we had this, let's say V, W. Okay, so remember we had this space. So we had this, we chose this, we took the orthogonal complement of this with respect to this, and then we got the gradients here. Right? Now, so there's quite a lot of flexibility of just changing this. I think it's kind of an interesting research direction, right? Because we can change something here, and we can get all kinds of different things. And people have tried all kinds of different things. So, and we are not going to discuss everything. But let's discuss, for example, we can take a matrix here. So let's say C is a matrix field, so symmetric positive definite matrices. Then this changes this. I want to do this like this. And so if we now we change the notion of orthogonality. So this will change the Helmholtz decomposition. Okay. Let's say this is bounded above and below by a uniform constant. Okay, so we make our decomposition. Now it's orthogonal with respect to this new inner product. Oh, this is a little bit unfortunate, maybe. I'm going to call this N. So we get a different space that is now orthogonal to this. You can kind of see why this happens, right? Before we had this, just gradient fields. Now we've got the inverse here of M. So we kind of need to compensate for this, because when we do this orthogonality in the inner product, this will cancel the M inverse with the M. But the statement is that now the minimizing movement schemes are not given by gradient fields, but are by fields of this form. Right, so these are not in general gradient fields, because we've got this. And so we have this decomposition, and so we can now go again and replace this V always by this. Right, and then put it here, and then do everything again, and compute the gradients and stuff. So this is then sort of this tangent space. So it's kind of different now. This might sound a little bit confusing because we kind of changed the tangent space. Let's say it's okay. We just changed it. And the upshot of this is that then the gradient operator, so we go through everything, the gradient operator, so it's now with respect to this twisted Wasserstein distance. So we don't have this anymore, right? We have now, so just to be clear, by changing this, we change this, right? So we have the set of probability distributions, we change the distance on it. All right, so we choose a different Wasserstein type distance. By changing this, we get a different distance, we get a different Riemannian structure, we get everything a little bit different, and we get a different gradient as well. And it takes this form. Okay, it's not very different from the previous one because just the matrix here came in. And this is the Fokker-Planck equation. So this is the Fokker-Planck equation of a diffusion of this form. So it's like if M is the identity matrix, and we are going back to the usual thing, because this will disappear. We got the usual Fokker-Planck we got the usual overdamped Langevin dynamics. Now with this M here, it's sort of a preconditioned version of this, and in fact, yeah. So you can do various things like with it. One interesting thing is, in fact, interpreting this X as a collection of many particles. And then this matrix M can introduce some correlation between these particles, and it goes into this Kalman-Wasserstein direction. I think we make a break, right? It's just too long. Let's just make a break. We're just going to pick it up here. Yeah.
Okay.
Yeah? Okay.
So 20 minutes or 15? Sorry? Okay, let's do 20 minutes. Break.
Okay.
So we start again at 35. 3:35.
I don't know, was it clear, or it's getting a little bit out of hand?
I think it's
Okay.
Yes.
Yeah. So you can have, this was kind of the next.
Worst
step,
case
but
scenario, your computer gets blocked. No, I'm
you
joking.
just need to have,
It just seemed very medical.